Our speaker tonight is Marty Moran. Marty has many years' experience in process control. He then went into reliability and asset management for many years. And then a couple of years ago, he managed to straddle both in the one plant. He's a graduate of the University of Illinois, Chicago, over 35 years experience in chemical engineering, process control, etc. He spent a lot of time in Houston, and his last major project was 4 years in Saudi Arabia, starting up the Sadara ethylene plant. And it's that which he's going to talk to us about tonight. Marty is currently based in Ireland, in Kinsale, and he has his own consultancy business. So obviously, if you're impressed with what he has to say tonight, you might consider taking him on. I'm sure he's looking for clients. And it's better I do, always, it's better I do the plugging. Okay, so without further ado, I'll hand over the microphone to Marty. Thanks, Marty.
All right, thank you, Killian. Hopefully our online people can actually hear us and see us. Okay, so this is what I'd like to do. First, I'd like to go ahead and introduce the project that I was working on in the Middle East. And then because multivariable control was such a huge part of this project, these were very complex applications. I want to first see the discussion with the basics of multivariable control. And then I have three examples that I'd like to work through. One is on a column, on a debutinizer column. And then the second one is what I'm going to call more an optimizing control. Simple application, but it makes money. And then the last one is a unique one that was done quite a few years in the past on a furnace. But more than anything else, what I want to do is seed the discussion for you so that you can be thinking about this as you're going through your schooling, but also what potential applications you might have. So let's talk a little bit about the plant that I worked in. Okay, so I worked at a company called Sadara. Actually got the shirt here today on. And Sadara was a joint venture between Saudi Aramco, which supplied the money. Everybody knows Saudi has lots of money. They supplied $20 billion to start the project, added another 10 billion probably later on, because I know they were all overruns. So they supplied the cash. The other JV partner was Dow Chemical. They supplied the technology and some of the people. Now, a project like this was mammoth. I want you to physically think about this, that a rectangle of 2 kilometers by 3 kilometers long, that was just full of entire process equipment. I think it was about $13 billion worth of physical assets that was actually in the plant. 26 process units. Half of those process units were the first time in Saudi Arabia. Now, there was so much pipe in this particular plant that the pipe would go from Cork to Dublin 10 times. There was enough wire to go from Riyadh all the way to London. At the height of the project, there were 60,000 workers on site from 120 different countries. So needless to say, this was a pretty big project that existed. Okay, so in the advanced control project was ACNO, Advanced Control and Optimization. And that project was both for the ethylene and for the aromatics plant. Now, in comparison to the ethylene, we won't worry about the aromatics. And so let's describe a little bit about the ethylene plant itself. I don't know how much familiarity you have, but ethylene is the building block for the entire chemical industry. So we had 12 furnaces, and these furnaces were about 10 stories high. 7 of the furnaces were devoted to gas, which was ethane. 5 was devoted to a light naphtha material, and those were the liquid furnaces. So because there's a coking reaction that occurs, a furnace would last roughly a month before it had to be taken out of service to be decoked. So we had 7 furnaces devoted to gas service. So that meant that 6 were normally operational, 5 to liquid, And because the liquid was a nastier service, you'd have either 3 or 4 that were operational at any one time. So the way that you really partition an ethylene plant is calling it hot, warm, and cold affectionately. Now, hot is hot. These furnaces ran at 800 degrees Celsius outlet temperature. Cold side in the fractionation section, you have temperatures below 100. So you have obviously a radical change from the start of the plant all the way through the plant. Now, what's interesting is that from a control perspective, the furnaces really weren't very interesting. They were just very practical, would be the way that I would describe it. Now, the warm section is a quench section. Now, for the reaction to prevent even more coking, you combine steam with the ethane through the gas furnaces, steam plus liquid feed through the liquid furnaces, and that's to reduce the amount of coking. So you have a tremendous amount of water through steam that's coming into the system. You have to get rid of that or the fraction. One of the major things is to remove. There also is a heavy liquid that's produced there. It's not very much, but you still have to pull that also. The back end compressor that's compressing it so that you can bring it up to the pressure for the fractionation section. The warm section also, we had multivariable control on it, but again, it wasn't all that interesting. Now we get to the cold section, things get really interesting over here. All right, so what we have here is a lot of distillation towers that are there. And so the first tower was a depropanizer. And this was the most complicated depropanizer I'd ever seen, and I'd run into quite a few of these in the refining industry. And then there's a debutanizer, which is pretty easy. You're going to see not quite that example, but something similar. We had a deethanizer. We had two deethanizers. It was an easy tower. And then we get to the demethanizers. The two demethanizers are getting to be more complicated. Now we're starting to get down to that minus 100 type of variable right there. Then we have the C2 splitter. The C2 splitter was one of the more interesting towers I've ever seen in my career. And I've seen a lot of distillation because the C2 compressor was literally part of the process. It was the top section after the vapor exited the tower, went through condensers, and then it took part of that liquid and it sent it back as cooling through the rest of the process. And then we pulled some off as product. So that one was just super, super interesting. And the reason multivariable control works as well as it does is wherever you have a lot of interaction, or almost impossible to do it very well through traditional controls. Then we had a C3 splitter. A C3 splitter is one of the most difficult separations in all of the process industries. It literally, because there's such a narrow difference between the boiling points of the two, liquids, the two C3 liquids, you require roughly about 200 trays. I think it may have been a little bit more. You cannot build this tower. You physically split those towers apart. And I believe there was a reboiler in the middle too. I don't remember quite. But the interesting thing about this is that if you make a change in reflux at the top, you will not see anything happen on that tower for the next 5 hours. So it's very difficult separation and great for multivariable control. Then you have this cold box heat exchanger, which is a very interesting piece of equipment. It has 6 inputs, or 3 inputs, 3 outputs. 3 are of the warm, 3 are the cold, and it allows you to get down to these temperatures that you need for the fractionation cold section. And the last part, already talked about the C2 compressor, but there's actually a C3 compressor also. Obviously, that doesn't get quite as cold as the C2, but it's a closed loop system. So that one isn't I mean, these are huge machines. Let me tell you, if you go see them, I mean, that machine would take off everything where you guys are sitting more if you look at the piece of equipment in the field. All right. So what is multivariable control? It allows us the ability to simultaneously control multiple hard constraints, those variables that we normally think about controlling to a set point. In the controller itself, it's really not a set, it's not a set point per se, it's a range, and you can collapse them together, then you get real set point control. There's a lot of flexibility in the way you set this up. And then multiple soft constraints. Now, the only difference between hard and soft are ranking that actually occur. So by manipulating multiple DCS controllers, most of the time it's DCS controllers. It doesn't have to be, but it normally is. And in a prioritized fashion to achieve the business and technical objectives. And should hit one more. Using plant-derived models. So that's multivariable control in a nutshell. Now, all of us are familiar with multivariable control. We practice it hopefully every day when you get in the shower. When you're taking a shower, you want to control temperature to a pretty narrow range. And you also want to control flow because you don't want to, obviously, had that in various hotels I've been in. That's not a lot of fun. But you don't want it to be a fire hydrant either. So you want some range. Now, temperature is a little bit more important than is the flow. And you do that by literally manipulating a cold and a hot water valve. In the parlance of process control, we refer to MVs as handles. So this is an interesting situation where it literally is the hand that's there. And there are certain disturbances that may happen, and I hope that doesn't happen to you often when you're in the shower, because this can cause a lot of different problems. All right, so that's the structure. Okay, so this is something I'm going to use throughout the rest of the presentation, and this is the structure that we want to think through these problems. And so what the first line in the controlled variables is going to be the highest priority. So temperature is the highest priority. Flow is the second priority. Now, manipulated variables, we already talked about those. And the disturbance variable is the water pressure that exists. Now, this is a model-based controller. And so what I'm showing is I'll talk a little bit later about how these models are actually derived. But I want you to think about these are the dynamic relationships for a normal change in a manipulated variable. So how do we read this? The rest of the presentation, these are the CVs in the columns. The one that's to the farthest to the left is the highest priority, and as we move to the right of the screen, they become priority. And then we have manipulated variables, hot and the cold water, and this is really the water pressure. Somebody pressing the toilet button there. So if we have a nominal change in the hot water flow, this is the dynamics that you see for the temperature. So there's a short dead time, and then it rises up, and we obviously increase the temperature from doing that. Same thing with flow. Short dead time increases up to flow. Same thing with cold water, except the temperature obviously goes the opposite direction. Now, down here for the water pressure, you have something that's very important. And that is, we start off at one value, we go through a dynamic change, and we come back to exactly the same value. It's called a zero gain model. They are very challenging to work with in real life. You often see them as part of a control scheme. And what would happen in this particular situation, normally running the shower is easy. You know, you got a 2x2 problem. Real straightforward answer that's there. But if someone presses the button, all of a sudden you want to be able to maintain your temperature and the flow. So it's going to start really moving around the hot and the cold water flows in order to achieve the objectives that we told it to do. And eventually it'll settle back to where it was originally because you have a zero gain model that's there. Okay, so that's the basics of control. Let's go ahead and work through our first example. This is a debutanizer. So there's 1,000 debutanizers. I've probably seen 100 of them myself in my refining work. Each refinery has 2 or 3 of them in there. So a debutanizer would normally this is a wild gasoline as it's termed. And the idea is to separate the light ends, which in this case would be propane and butane, from a gasoline stream whose vapor pressure has been adjusted. Now, in any distillation tower, we normally control both compositions at the same time, at least in a theoretical fashion. However, in real life, there will have to give up on one and only control the other. There actually is a priority between the two. And because this gasoline stream is going to a certain tank, it can't take high vapor pressure. So it is the highest priority compared to the propane butane stream on the top. And I want you to remember that because we're going to talk about that in a minute. That's the general 5+ stream. Down here, this would be a vapor pressure we'll talk about in a minute. So the feed comes in off the bottom of the propanizer, goes through exchanger, enters the rectifying section. The DP that's here is indicative of flooding for this particular application. Then we have fin fan cold water at the top, very standard. Pressure is controlling the off gas. Then the product is just level control valve going straight out to storage. And then we have a reflux flow controller right here. So at the bottom of the tower, this temperature, we're going to take that temperature and calculate pressure compensated temperature, because we're actually going to move around the pressure potentially. And the bottom of the tower has a fired temperature. It's the standard cascade you see for fired reboilers. And this is a safety issue. We must stay purge temperature, and you'll have on any furnace many different constraints that you potentially have to deal with. But for there's something that this is where you start to get into real subtleties and control. Now, I want you to think there's a little mental experiment I want us to do. If we change reflux and we have a temperature to pressure cascade right here, we increase reflux, liquid comes down the tower starts to cool a little bit. This temperature, it sees this temperature going down, comes down through the furnace. The temperature controller senses that my temperature has gone low. What does it do? It adds more heat, bring it back up. What you end up doing is almost a zero gain effect temperature right here, which means that reflux cannot be used to control this particular temperature or composition at the bottom. That for multivariable control is potentially a big problem. So the way that I would probably set up this application is to write to the pressure controller. I'd break the cascade to do that. And the reason being is we do the same mental experiment, increase reflux, and we've just got the pressure controller here. We just have a constant amount of heat going in there. We'll have a linear model at the bottom instead of the zero gain thing. And it now gives us another handle to potentially work with. So, that's the basics of the tower right there. Now, the word control. Word process comes first for a reason, because it's the more important of the two words. We must understand the process before we can do the second part of that, and that is control. So one of the most important things that we do on a project, and at Sadara, we went through this many times. This is a simple example. We went through this many times where we had to make sure we got these exactly right. As we talked about this example, safety comes first. We're not burning down the furnace. So we got to keep that, we have to keep the furnace arch temperature below its high limit. Next is an operational issue. We can't run a tower if it's flooding. So it's the next priority. And they are in exactly that order, right? Then we get to the composition at the bottom of the tower. We already said that that was more important than the top composition. And the last one, we know from your chemical engineering that if we minimize pressure on a tower, we can reduce the energy consumption for the tower. So if we actually have an extra variable, maybe let's go ahead and reduce pressure on the tower. So this is the list of priorities. Towers like the C2 split, the C3 splitter, the list of this about 3 times longer and entailed much debate with the operations people who honestly kept changing their mind because they didn't understand how to work. And so it took a while to work through it. But at the end of the project, everybody's truly on board. Now, we go from this structure, hard constraints, the order I talked about, arch temperature and flooding. Controlled variables are, now controlled, I mean roughly to a set point. These are the 2 compositions. Then manipulated variable, okay, it's a little bit older presentation than I originally had, but so I kind of changed it and saw my own error in there, but let's not worry about that. So we had reflux, and then I adjusted it and changed it to be the furnace fuel gas pressure there. And then there's a disturbance variable, feed rate. The feed rate comes wild to us from the bottom of the dipropionizers. We have no control over it, but we need to adjust for it. Okay, so now we need that you're very familiar about mathematically, but becomes very, very important in a control context, and that's degrees of freedom. If you have regular basic controls on a tower, like you're using reflux to control composition at the top or temperature control at the bottom, those are what we call SISO controllers. Single input, single output. Fairly straightforward, really, from that perspective. We're now in the MIMO world, which we have multiple inputs and multiple outputs. So in general, we have 3 cases. Those cases are, we have the number of MVs is greater than the number of active constraints, plus the number of things we want to control as set points. Now, active constraints actually mean something because constraints can be there. We may be close to flooding, or we may be very far away from it. Same thing with the arch temperature constraint. So if we have more MVs than CVs and constraints, this is nirvana. We can all of our CVs and their constraints, and with any extra degrees of freedom, MVs that are left, we can move in a direction that we want to. In this case, it would be pressure. If we have a square problem, then we can solve the problem the way it is, but we lost that ability to use those extra MVs because they're needed for control at this point. Now we get into the life is tough situation where we have less MVs than we have active constraints and CVs. And this is where this prioritization becomes super important. It meets the hard constraints first and then goes through that order that we have there. Now, I always train engineers that we're going to put this grid together that shows CVs versus MVs and DVs, because these are the pairings that we actually have. And we now put our process hat back on. We really spend a lot of time to think through the process side of it. Instead of getting to the exact model, I train engineers. I want you to think in terms of this is a strong handle, this is a medium handle, or this is a weak handle. So let's just start at a conceptual level there. It made it a lot easier to work with the operations people because this is stuff that they live and breathe every day. So let's start with our strong models first. Okay, so if we look at, and this is the same structure that we were talking about before. So our most important priority is the furnace arch temperature. And so it's the highest priority flooding and then the compositions as we move on over. Arch temperature only is affected by the furnace. So that one's really straightforward. Flooding is everything kind of affects it to some degree. And the models will show it later on, which is the strong or weak medium handle, etc. I just put this up there for purposes right now. And then the bottom and the top composition, those are exactly the way we control the tower in real life with SISO controls. Now it starts to get more interesting because we add the medium models in there. And so flooding becomes interested in the sense that just about everything affects flooding to some degree, and we could use those in some combination to control flooding. Then over here, now this is kind of, depends on how we configure the loops. The top composition would be affected by the furnace. If we leave the temperature controller, temperature pressure cascade, we lost that handle up at the top. If we break it, we would get this one back. So after we go through analysis like this, we would see this hole and we'd probably say, nope, we want to break that cascade that's there. And here's the DVs. Feed affects just about everything. We know it's going to affect flooding. It's going to affect the, we're going to want to correct for that later on. We have a couple weak models, and that is pressure, tower pressure to the compositions. Now, we don't normally control tower pressure. I don't use tower pressure to control composition, but it does have some effect on it, and we want to know what those effects are. Okay, so now we get to the models part. And it's again the same structure that we were just talking about, where we have arch temperature, flooding, and the compositions over here, reflux temperature or fuel gas pressure, and then feed. So the idea behind the models is exactly the same as we just showed for the shower example. For a nominal change in the MV or the DV, what is the dynamic effect? But you really start to see some interesting changes. Look at the flooding that's here. You have for reflux a very short dead time, but on feed you have a long dead time. That makes sense. But you also have here bottom's temperature maybe takes a little bit longer. Until you actually do the models, you don't know what they actually look like. But you'd have differences along here. That gives the controller some abilities to work with. Up here, this bottom's composition model here, if we had left that temperature controller the way it originally was, we'd have this zero gain effect that was here. Even though it wasn't our handle for us on a steady state basis, it's still a handle for us. We have to still incorporate a dynamic effect. That's why we'd probably break that model and go ahead and make it a more linear combination. So in real life, how does it work the way it's structured? Use the furnace. There's no other question about that. All composition control, everything else ends up being secondary. Flooding, we have lots of possibilities that are here. We could use pressure. We have a pretty decent handle. And that way we still have reflux and furnace temperature here for our compositions that are over here. So you can conceivably get a situation where flooding is handled primarily through pressure, and we use our remaining handles over here to control our compositions. Now, one thing we would probably do is that even though these are defined as MVs, the modern controllers have the ability to make these a DV only, so that you could set it up such that I don't manipulate pressure to control composition. So you get to all these interesting possibilities. And so what I train an engineer to do is look up and down here to see what would possibly be used to control that particular variable. Also look across as to what does MV touch, because sometimes go away and you end up with some very interesting combinations. This is a small problem. When you get to the much bigger problems, you can't predict it ahead of time. That's the problem. That's why you need a really thorough process analysis. Okay, so let's talk a little bit about how did the models get created. There are automatic step testing programs that are actually done. You start with a seed model. From that seed model, we actually literally turn on the controller the way it would control in real time. But it's a seed model. It's not a perfect model. It actually does a pretty darn good job with it, to be honest, which is pretty amazing. So we start with that, and then what happens is we have this algorithm that move it down by 10. It has all this different perturbation it does with all of the MVs at the same time. So you're just superimposing these moves on top of it. And you'll leave that algorithm or leave that running for a week or 2 weeks. It creates this tremendous data set for you to go ahead and analyze. So you go through a model identification process. There's obviously you got to massage those models, you got to get the junk out of the models, etc. And then you get to the model review process. Your model review process is going to depend heavily on that analysis that we were just talking about by looking up and down the columns and the rows to make sure that this is doing what you think it's going to want to do. We have a sanity check, and it's a very important sanity check. 75% of the projects in this step right here, doing all the testing, putting the models together. Okay, so that's the debutinizer. I have 2 more examples I want to go through. One is, this is a simple hot oil symptom, and I'm going to call it really a optimizing controller, if you will, because it doesn't really have a set point variable associated with it. Let's say that we gave an operator the task of looking at the system and only, choosing this temperature set point right here, such that any one of the controller outputs doesn't, it has room on those controller outputs. So let's step back and let me talk a little bit more about this. This is 6 parallel exchangers. Let's say there's 6 towers that are there. Temperature controllers on the process side who adjust it for distillation reasons and doesn't know anything about the utility side. There's a DP controller over the top part of it, keeps the in a range. They don't back out at one end or the other. Same furnace as before, and it has the same temperature constraint that you had. So if you gave an operator the task, all that he does all day long is look at that and keep reducing the temperature, when there's room to go do so. Let's say that the maximum controller output right now is 70% on one of the valves. So hey, we can go ahead and reduce that a little bit. We reduce it. 20 minutes later, we'll look back. Oh, he's up at the 72%. Heck, we can go a little bit farther. Now we're at 74%. Continues on. All of a sudden, we get to 90%. Yeah, I think we're kind of there right now. And we want to back. Oh, 92. We need to increase it a little bit. Then all of a sudden, that particular tower doesn't need as much heat. Somebody cut its feed, so it went down to 50%. Now we go look at the next most one is 70. Yeah, we can go down a little bit, so it can ride a different constraint that's there. I mean, that's the general idea behind it. So again, same arch temperature constraint. We just talked about minimizing it. The outlet temperature subject to the controller output constraints. And we also should keep the DP in range also. So we have the hard constraint, which is furnace arch temperature. I probably would not call that controlled variables. That's really a soft constraint, is what I'd probably call that. Now, you're not used to seeing controlled variables or CVs as temperature controller outputs, because that's not normally the way that you would think. But you can do tremendous amount of very good things using multivariable by looking at when does a valve go wide open or closed and take advantage of it. And variables, the furnace outlet temperature. And so in that particular application, all it's going to do, it's a simple application, but it will optimize and only put enough heat into that furnace ever, right? Compared to what an operator doing. Most things like are totally forgotten about, and they just waste money is what they do. So it's a simple application. Okay, so let's start here. Okay, so this last application came out of an ammonia plant. This is in the panhandle of Texas. And the ammonia process is 2 key pieces. One is the reaction section, which is the ammonia or I mean, is the hydrogen plus the nitrogen. But the front part of the process, you have to produce the hydrogen. And the route to hydrogen in the process industries is typically steam methane reforming, but there are a couple other processes that exist. This is a mammoth furnace, runs at temperatures very similar to the ethylene furnace that we talked about earlier. So let's talk about the inside of the furnace first. Okay, so this furnace, every one of these red lines that you see here is a bank of tubes, of 40 tubes. So it's a bank of 40. There are 9 of these. So there's 360 tubes in here. Now, the way I do it comes at the top, goes through distributor, all the way down, goes into collection at the end, comes out the furnace right there. Now, when we went to kick off this project, the guy said to us, "Hey, it's great that you're showing up here to do control, but that's not my big issue. My big issue is this furnace, and the problem is that we have maldistribution of temperature inside the furnace that causes tremendous degradation of tubes as they get to higher temperatures. And we'll make you a god if you can go ahead and help us with that." And I said to him, "We can help you." We did applications on crude oil furnaces or any refinery furnace, so it's called temperature pass balancing, where if any pass gets a little bit too warm, you'll put more fluid through it till you balance the temperatures on each of the passes. So that, before I describe that, let me just talk about the bottom part here, and that's actually the controller. We have a temperature controller going to a flow controller, and then we actually have 10 fuel gas passes. And what you'll see is that the fuel gas is on opposite sides of every tube. And there were literally 10 different pressure controllers the operator could change the pressure set point on. So that's the layout of the problem. So what I suggested we do is look at delta T's between each of the different collection tubes. And so what we were looking at is T2 minus T1, 3 minus 2, 4 minus 3, 5 minus 4, etc. So what we really wanted to do was drive those to zero, the delta T's to zero. Now, because of the way the algorithm is structured, you can't just do that, because you could solve the problem and instead of being flat, it'd be like this. So you actually have to add a couple more in. So what we did is we added 5 minus 1 and 9 minus 1 to truly, and it actually weighted those a little bit more, so that it actually drove it down. So if we look at the structure, oh no, let's do one other thing first. Okay, so let's go backwards for a second. All right, so what I want us to do is a little mental experiment. If we're looking at 2 minus 1, we increase this pressure, we're obviously going to drive T1 up higher. We're over here on 3. If we increase that, it would drive 2 up. Now, the one that's in between it's dicey. We don't know what it would do. And actually, you might even zero that out because it might be so close to one another. One time we increase it, another time we decrease it. So we zero it out. But the structure of that is, let me do something. Okay, so I'll tell you what, since we got this already up. So the way that this was set up is that the control variable is still that main outlet temperature. We're going to adjust the, I'm going to call these soft constraints, or all the delta T's, or actually 10 of the delta T's. And then down here, we have the main, this is the flow controller that was underneath the temperature controller, and then the 10 fuel gas pressure controllers. So we have a 11 by 11 problem, which means we should be able to solve this completely. And I'll go back to, this was the delta T portion of the problem. So we have 2 minus 1, 3 minus 2, 4 minus 3, etc. So as we just described, 2 minus 1, pressure 1 affected that, pressure 3 affected it. And I have a red X for the other one just because that's a little dicey. We're not quite sure about what it is. And so you can see that most of this matrix is sparse. Most of it is zeros, because if we move the first pressure, it's probably not affecting the last tube on the other side. And we probably don't want to do that from a control perspective anyways. So we would zero that out. let the big handles the action. And then when we get 5 minus 1 over here, these start to affect the outside of the furnace and the middle portions of the furnace, depending on which one of these two that was there. So that's the layout of the problem. So literally when we turn this on, within about 3 hours, the entire furnace flattened out and stayed there for the next 20 years. Give me a little bit of a royalty for that application. I'm thinking maybe I wouldn't be talking tonight, but this shows you the power of control, that you can take what seems to be a problem that you wouldn't pay much attention to, but you can go ahead and solve it in very unique ways. So before we conclude, I want to step back and talk a little bit about the benefit side of this. All right, what are the benefits? One of them is just because of the predictive nature of control. I want you to go back to the debutanizer example for a second. An operator has a model in their head when they run the units. But on that debutanizer, in order for the human to be able to comprehend it, they'll only make 1 or 2 moves to a tower an hour and wait for it, because they know what they're expecting to have happen. The human can't comprehend the idea of moving the reflux up by 5 barrels this minute, another 3 minutes down the road, down by 3, up by 4, and then trying to figure that out for 1 MV. That's a hard problem to do for the human. I can't do it. Now, if we add that to all 3 MVs and do this simultaneously, there's no possible way I could figure it out. But what the computer can do is fantastic, because it has a picture of the model already from what we went ahead and did. There's a bias calculation that runs before the calculation gets to the control part when it chooses the MV, so it updates its model automatically as part of it. So just the sheer calculation efficiency of the models is so superior to any human. And what humans do is the only way they can possibly handle calculate something like is they build in these huge safety margins. P5 composition at the top of the tower, its actual limit might be 1%, but they at 0.5%, whoever gets to 0.6 out there making moves. So they build in a lot of false constraints into the problem. What control does is comes and shatters all that and says, hey, I can run up to 1%. And it will gladly push limits like that. And that is probably multivariable control. Its ability to reject disturbances is better than any basic control that exists. Now, basic control you can do quite a bit with, but multivariable control can ride out big big upsets much better than the basic controls that are there. Now, often what you see is operators taking controls off the basic controls when that happens. But its real payoff is this ability to run up against constraints. To give you one example from a refining example, a fluid cat cracker is one of the major conversion units in a refinery. And one of its constraints, it's either 1 or 2 constraints. One of them is what they call an air blower constraint, where an air blower is a volumetric machine that is used to burn the coke off the catalyst in the regenerator. And what happens is that as night comes around, like now, air gets a little bit cooler. A certain volume, we can get more mass into the regenerator. So what you literally see, it's almost like what happened in that optimization problem for the hot oil, utility. As the temperature starts coming down, the feed will start to rise, and it will just kind of have the sine wave. It's a beautiful thing to watch, honestly, because it's just so adept. Because all it is a calculation machine. Every minute, gladly churns out all these calculations and makes these small little moves that end up being 2 to 5% extra feed into a unit. And so you didn't add any more steel on the ground, and all of a sudden you got 5%, or maybe not 5%, but a few percent more production there. So that's kind of the big benefit that you get there. And it trades off constraints. We saw that in the hot oil example that's there. So variable control can be used for many different industrial problems, and not just petroleum or oil refining. There's a lot of places. You have to define the process priorities first, as we did. Translate those into CVMB-DVs. We have to go conduct those step tests. And then last, commission and train the operators. And with that, you have reached the end of the formal presentation. I guess we'll turn it over to